Yes, so it's about time. I think we have quite a good number of participants. So this is a Rust lecture, and over to you, Adam.
Okay, so hello everyone. Before we start the actual lecture, I have a quick question for you. How many of you has any experience with Rust? And furthermore, how many of you have actually built and deployed something written in Rust on the internet computer? Yeah, you can write in chat. Okay, so I think I can assume that no one has any experience with Rust. It's good that I've prepared some basic information about Rust in general. So okay, so before we go with the tests, if you think about Rust, so the Rust was created apart from the IC, actually, I think 5 or 6 years before the IC was created, the Rust was already there. And its main purpose was to make a C developer's life a little bit easier. So its main purpose is to be as low level as possible, as close to the bare bones and the memory and the CPU as possible. Maybe not as close as assembler and C, but still. The main difference between Rust and C is that Rust comes with the idea of owned variables. So this is actually pretty big idea. Most of the learning with Rust is about the borrowing mechanism and mutable borrowing and other stuff. We will not talk about it today, as it is not the scope of this lecture. So going forward, why do we need tests in general when we do anything with the computer? So the main reason is that we need to have a way to check if the program, canister, or anything that we've coded, we have created, is actually working properly. And of course, we can test it in a production environment with actual users. But when we start to store anything of value for the users, then it becomes quite troublesome, because if we made some errors or some bugs or some ways for others to exploit our code, then we will lose this value and we will lose the trust the people has put into what we have created. So apart from storing value, we need to understand that when we create and deploy anything on the internet computer, it's actually equivalent to running a program on your PC, with this small difference that this program should be able to work forever. So if anyone of you has ever used Windows, then you know that it cannot be run forever. It needs to be rebooted quite frequently. And when you reboot a program, a canister on the IC, when you reinstall data, because the reinstallation of the canister code is the equivalence of rebooting a computer. You will lose all the data that it was stored unless it is stable. And since now we do not have any simple way of like backing up the canister and all of its data locally, so we need to make sure beforehand that the canister we have created, the code we have created, is bug-free. Well, let's say as bug-free as possible. It's not really possible to make completely bug-free code. Another part is that when you have an issue, when you have a bug that occurs in production, without tests, it is really hard to find it locally, because usually those problems occur only with the data which is in production, or which we do not have access to. So it is really, really hard to fathom a way to replicate and find where the bug is occurring. As I have mentioned before, we have option to upgrade the code of the canisters. However, it is not always possible. The reasons for it can be many. The most important thing is that we do not always have the luxury of upgrading canister. So we need, once again, we need to make sure that the code we are publishing is as well polished as possible. And the last but not least, but also really, really important, when we are at the beginning of the development cycle, the testing what we have prepared by hand, like deploy canister locally, deploy the UI, click, find the bug, and then go back to the code, it takes a lot of time. So preparing any canister will also take a lot of time, and that's why we need tests. I think I didn't mention it at the beginning, but if you have any questions, just write them on the chat. I will try to answer them immediately. There is also a scheduled Q&A at the end of the lecture. So if any of the questions are not answered during the lecture, I can answer them in the end. Okay, so let's go to the next slide about the development cycle. So it is not like the usual development cycle. I've tried to make it as icy as possible. So without tests, we first have a code development, then we are uploading it to local replica or IC if someone wants to do it. Okay, if someone wants to do it already on the network, then manual testing or testing with prepared bash scripts, which are quite slow. When you find your issues or bugs, then you need to look for error in the code, which takes time. Then you try to replicate it, and then you try to think what were the variables and what has happened, and spend a lot of time on it. And in the end, fix the code. And after everything is done, let's do it again, because not everything can be fixed immediately. And sometimes while fixing one bug, we're introducing another. So with tests, we can strip all the part with uploading anything to local replica or to the IC. We just develop the code, develop the tests. There are people that actually like to develop tests first and then develop the code. Then you can quickly run tests inside your IDE, so no need to go to browser, shell, or any other thing. For most of the part, you can actually debug code in tests, so you can see all the variables. You can place breakpoints to see what's happening and why, and fix the code. And at the end, the bonus thing is that after fixing your bug, you can play all your tests and see if nothing else was broken while you were fixing the current the current bug. So it's a lot faster. My experience is like 50% of the time between Motoko and Rust was spent on trying to find bugs in Motoko, trying to find why something is not working and trying to repair it, and battling with the code all the time. Just to answer advantages of Rust over Motoko. So it's the next slide. I hope it will be quite exhaustive. If not, of course, please ask questions in the chat. I will try to answer them immediately. So my story with Rust is rather funny, because I've started to look at Rust for the IC because my IDE had no tooltips for Motoko. And actually, I'm quite used to them. And it was so bothering for me that there is no tooltips, and I cannot quickly see what properties any given structure has, that I've started to look at the Rust. And when I've started to play around with it and read documentation as possible, I found out that there are several advantages of Rust over Motoko. And yeah, it is most loved, but also most dreaded. As I said before, Rust is a well-established language, which was created before the IC. Lately, even the creator of Linux, Linus Torvalds, said that he is considering including Rust in the development of the Linux kernel. So yeah, we can say it's quite stable. Because of its independence, we also have thousands of ready cargo packages. So if you're trying to, I don't know, calculate some hash, or maybe use some cryptography function, you know, convert images, convert audio, read some weird file formats. For most of those things, you will find ready cargo crates for Rust. So you will not be forced to implement it by yourself. You can see all crates under crates.io. Also, crates and in general cargo system you can use it similar to NPM. So you're writing the package name, specifying version, and the cargo will automatically download it for you from the internet sources and link it with your program. So it's really easy to use. Another thing is that with Rust, as with C language, you have more control over memory and computation. I see it as a plus. Many will see it as a minus, because it requires from the developer much more than when you have a garbage collector. You need to think about what's on heap, what's on stack, what is heap and what is stack. Also, Rust imposes on you thinking about which function owns the variables. So yeah, it is more taxing on the developer. However, it gives you much more possibilities to make better code, linear, faster. As I said before, no garbage collector. And I know that when you want to develop something fast, garbage collector usually is the nice thing to have. However, the problem with it is that it makes your program not 100% could say you cannot really say with certainty what exactly is happening and when, because garbage collector tends to stop your program, like collect garbage and then resume your program, and because of that, it's not you are not in full control. Also, Rust have really extensive documentation. I've included some links for Rust at the end of this lecture, so you can go and check it out yourself. I'm in my daily work with Rust, I'm using Rust dots with documentation for most of the libraries. And it covers all the functions, all the traits, and it's not like just a function name and what it does, but also with examples, so it's easy to use. Another part why I have chosen Rust is that it gives you more internet computer features than Motoko. I'm quite sure that with time, Motoko will be expanded to include those features. However, right now it is not possible. And two of them, which are the most important, is in Rust, you have access to stable memory. So in Motoko, you can assign variables as stable, but only basic variables can be signed as stable. So for example, if you create equivalence of hash map, you cannot mark it as stable because Motoko doesn't know how to serialize it. In Rust, stable memory is seen as an array of bytes. So we can write any arbitrary data to stable memory. And after the upgrades of the canister, we can read anything from it. So you can see something like a save game for a game, or maybe database file for some SQL database. Anyhow, you have full control on what you're writing there than what you will read from there. So yeah, it's quite powerful. And another part which is not accessible to Motoko is inter-canister calls using proto-buffers. And why we even would like to use it is ICP ledger has multiple functions accessible only by proto-buffers. You cannot call them from Motoko. And let's go to the two last things. You have established testing framework, which is actually past part of the Rust, which I will show in a moment. And you have quite good IDE tools and support for the Rust language. Oh, that's yeah, that's actually really nice that they're adding to Motoko. So as Sebastian has written, there is already experimental stable memory in Motoko, which is great. I hope it will be possible to use it, because then we could have a possibility to switch from Rust to Motoko and from Motoko to Rust on demand, which is always something good. Okay, so right now I do not have any like a comparison Motoko versus Rust, but if you guys want, I can prepare something for you guys and make it and share it via the Motoko Bootcamp.
You want to, sorry to interrupt, you want to compare the WASM size of Rust and Motoko?
No, not the WASM size, just the pros and cons of Rust and Motoko. Because in this lecture, I've focused on Rust and why I've personally chosen Rust. However, I think that it would be nice to have like a comparison of the two of them.
Yeah, sure. Right.
Because those things I've said that are cons, they're my personal cons and pros, and I believe that not everything is applicable to everyone. Okay, so before we go to the testing part of the Rust, I think there are some few more important stuff that we need to cover. just to make sure that we know what's happening. So either way, if we are using Rust or Motoko, both of them are compiled to WASM. And this is a shortcut from WebAssembly standard module. And what's uploaded to the canister and what's actually happening is the WASM file. You can think about it like one big exe file on Windows or one big package on Mac OS X. So because Motoko was created for the IC and Rust was not, in order to have any interaction between the Rust code and IC, you need to use package ICPSquad. It's already created that you can download using Cargo, so no problem there. Actually, when we are working with Rust, you will be using two packages. The first one is ICPSquad. The second one will be ICVASM optimizer. I think it's called ICPSquad optimizer. And we'll get there in a minute to why you will need it. So another restriction, which is right now imposed on the whole internet computer, is that a single HTTP call needs to be below 2 megabytes of size. And basically that means if we create any canister, either in Motoko or in Rust, it needs to be less than 2 megabytes. Answering to Sidecut, yes, I have, and there is a way to mitigate this problem. If you're interested, I can show you how it's working in the question and answers section. Okay, so going back to the lecture, and this WASM size, it's not only applicable to the canisters. Actually, if you are sending any information to the IC, the single part must be less than 2 megabytes. So, for example, if you would like to upload a movie that's like 2 gigabytes, you would need to split it into 2 megabytes parts and send it part by part. And the last important thing is that canister upgrades, they should be tested and they should be working. Because if you're lucky, you will simply end with a canister that cannot be upgraded. So probably not so lucky, but also not so bad. If you're unlucky, you can break your canister. I know this shouldn't happen, however, it sometimes happens. It's really frustrating to break your canister. And because you cannot right now easily backup data from your canister, then there is some possibility that you will lose everything that's there. So if for example, like us, you are creating an NFT canister, sorry, which will store NFT data and people actually trade those NFTs, it can be quite troublesome to lose all NFT data. Okay, so if you'd like to run Rust on your computer, it's actually quite easy. All you need is, if you're using Ubuntu, is Rust C package, sorry, which will install almost everything that you need. If you are using other Linux distributions, most of what I have used also have an equivalence of Rust C package. There is also Rust C installer for Windows and Rust C installer for Macintosh. So I think you would need to use really weird or old system not to be able to install Rust compiler. Yes, you can use Rust app, which is, well, it is recommended because apart from just the Rust C, it can also install targets, and we'll get to it in a moment. I need to get some water, sorry. Okay, I'm back. I apologize. Let's resume. So Rust compiler has a possibility to compile your code to different targets. So I think the best way to describe targets is like completely different types of computers. So we have like PC computers, which would be one type of target. You have mobile phones, which would be another type of target. And you also have WASM target, which is WebAssembly, which can be run directly on browsers. And it is important because WebAssembly was created for browsers, but right now it is being repurposed for other stuff like Internet Computer. So the target we're interested in is WASM32 unknown, which will create a code that can be run on IC. The library type must be cdylib, and only this library type will work on IC. Our Rust code, we need to treat it with IC CDK optimizers, because CDY library contains some common code, and it makes it quite big. So the smallest CDY lib that can be created is 2.2 megabytes, and it's already too big for the IC. So we are using the optimizer to strip the unused code. Okay, so I think that we have covered some basics. If you have questions, of course, please ask them. If not, we can go directly to how tests are working. So when you create any code in Rust and you'd like to test it, the code on the right side is like the basic thing that you will need to use. And lines that start with a hash are processor directives, which can cause several things. But the most important for now is that the first line will cause our test code only to be included in the output when we're actually testing. So if you deploy the whole code later to the IC, all the code for test will not be included. So we can make them as big and as extensive as we would like to, and it will not influence the size of the output code. Then we use the third line is responsible for giving access to the functions we've written, and it's if you want to understand more why you need to write it, then you need to read a part about canisters and modules in the Rust documentation. And the last part is the actual test, which is line hash test. And then we go straight to the test writing. We already have two more preprocessor directives which are accessible to us. The first one is should panic. So we can write tests that needs to pass, but also we can write tests that we know that will fail. So for example, if you would like to make a test for NFT transfer that we know should fail because it is initiated by someone other than the owner, then we can mark this test as should panic. And if the test panics, then it's okay and it will be marked as okay. And the last preprocessor directive is ignore. It's in a situation when we will create a test that takes a lot of time to compute, and we do not want to run it every time. We want to test the whole library, because the idea of having tests is that we can run them and have the results quickly to see if we are heading in the right direction. Okay, so once we are start writing tests, we have a possibility to check if everything is okay. The code here is the actual test. So yeah, if you like, you can try to run it and it will work okay. And we have three basic types of assertions. The first one simply works on a Boolean expression. So the result must be either true or false. If the result is false, then the whole test fails, and we can see it in the result. And the example of this assert is in the last line. We can also check if left and right parts are equal or not equal. So both assert equal, assert not equal. And you have also examples in the middle of both of them. Important thing about Rust and the Rust language and the Rust syntax in general. Rust is considered to be like a really expressive language, which means that every dot and every semicolon counts. And because of that, it is easy to make errors, but also you can do many wonderful things in just a few lines of code. And as you can see, all those assert equal and assert NA are ended with oh shit, I just forgot how this sign is called in English.
You mean the exclamation mark?
Yes, exactly. Yeah, thank you for that. Yeah, they're ended with exclamation mark. And exclamation mark means that the whole part is a macro, which works different than a function. What macro does, it actually, before the code is compiled, it substitutes the whole part with the actual code. And they are used for several reasons. Oh, it's also called the bank. I think I will remember bank. Yeah, but it's important to know that you're using macros because they're harder to debug and harder to check why it is not working. On the other hand, they give you much more flexibility than functions. Okay. Another part that's actually quite interesting is the principal part here. I think you're already used to principals from Motoko. In Rust, there is also principles and many other basic structures accessible via the ICPSquad. So yeah, use it. Okay, there is also, because this part of the test is like a regular test with asserts, you can quickly check if something is working or not. However, it's not exactly easy to use it, because most of the time when you're working with Rust, you're also working with results. So for those of you that have some programming experience, you're also encountered nulls and null pointer exceptions. In Rust, there is no notion of null. You only have result, which can be either OK or error. You also have an option, which can be some or none, but you never have null. And because of that, most of the function returns are actual result, which are usually something like this, which the first part means nothing, that there will be nothing here, and the second part means that the error may contain some string. Of course, both of those types can be changed to something different. And because results are so heavily used in the Rust everywhere, it was also given a possibility to use a result as the output of test. So when you are using results, you are not allowed to use asserts because they panic and it will not work properly. However, if your test returns OK, then the whole test is treated as correct. If your test returns error, then it means that the whole test was error and the output will show errors. So once you have written your code, you have written your tests, in order to run them, all you need to do is write cargo test in your shell, bash, command in Windows or any other terminal. And it actually works pretty fast. I can show you in actual result. It compiled the whole code and then ran several tests. So if anything has changed, you simply write cargo test, and you can immediately see if everything is working or you've encountered some errors. Another really nice part is that when you're using an IDE, I'm personally using VS Code, which supports Rust, you can run tests directly from IDE. So you do not even need to open the shell. You can just click run test and see if the result is okay. So in VS Code, you have option to run or debug tests. The bug part is really, really nice and important because we can place a breakpoint, click the bug, wait a bit, and then we can see all the variables in here that were created. So you can check the state and see what's happening, what's wrong. Then you can step over or into, so like go to the next line, see what has changed, go to the next line, see what has changed. Oh, I need to zoom in, sorry. Is it better?
Yeah, it's better. Maybe a bit more, if possible.
Yeah, of course.
Yeah, I think like that, yeah, it's okay.
No problem. So once you're in the bug, you can check all the variables. You can step over to the next line and see what has changed. If there were errors, you will see what was the error and what were the variables when those errors occurred. So the actual finding of the bug and fixing it is so much faster. And because we didn't upload it to IC, we've reduced several steps in order to find the bug. Yeah. So let's just finish the debugging session. Of course, you can place the breakpoints anywhere in the code. In here, I've just placed it a breakpoint inside a test. I can navigate to something other, place breakpoint. When I go back, I can simply once again invoke the test, debug, and it will automatically stop in the place we were interested previously. So it's much more like we would be working with JavaScript, that you can place breakpoints either in IDE or directly in browser. So the whole development cycle is so much faster. Okay. Another option for the test is there is included Test Explorer, which gives you like a list of all the tests that have been created. You can either run them by package or individually. And they even will show you green statuses or red statuses. So it also helps you to check if everything is working. Okay, I've prepared some links. I think we will somehow share it on the Discord so that it is easily accessible to you guys. I highly recommend reading IC Rust Introduction and Rust on IC Good Practices, because it contains a really condensed knowledge about specifics on running Rust on the internet computer. Okay, so we are right at the question and Q&A. Okay, so yes, exactly. When you so the question is, can you explain how to import Rust canister to Motoko? Does the Rust canister import be done as an actual model? Yes, exactly that, because all the communication between the canisters is always encoded by Candid or by protobuf. If we encode it by protobuf, then only Rust canisters can use it. By default, it is written as Candid, and any actor on the IC can call it. So in order to call Rust canister from Motoko, all you need is to specify the interface, like you would specify a Motoko interface, and define it as an actor and just call it, and it will work. There is no nothing more special needed to do. Okay, yes. What approach might you suggest for installing a SaaS platform into the IC? The SaaS original code is written in Java. Might the Java code be largely translated to Rust? Compiling Java to Wasm? I think the best thing would be to try to compile Java to Wasm, because if you like, I haven't seen any compiler from Java to Rust directly. There are completely two different languages. There might be a possibility to compile Java to Rust. If so, then yeah, as long as you have the Wasm file, you can install it on the IC. However, without the proper annotation of functions, the IC will not be aware of what can be done with it. So any queries or updates will not work unless you properly annotate them. The problem with Java is that I haven't seen any ready package to facilitate communication between the IC and Java. There might be some in progress, or maybe community is working on something, but I haven't seen it. Also, I think Java garbage collector might not work properly on the IC. That would need to be tested. Okay, how you handle the large VASMs that exceed 2 megabytes limits after optimizing? So it is a little bit tricky, and I will show you a code in a minute. But basically, you create a canister into which you will upload the big VASM file, split it into parts. And then this canister invokes the methods of creating or uploading data to another canister. So you need to have two canisters. One is like the uploader deployer, and the second is the target canister. Let me just look at the code. Okay. Actually, this one is written in Motoko, and I found myself that if I want to prototype anything fast, I'm using Motoko, and then mostly I'm rewriting it to Rust. And yeah, you have a stable variable which will contain canister VASM, which is an array of not 8. You have a function to upload VASM in parts. So every time you call append VASM, you send a part of this big, large VASM, and then you append it to an array. And the last part is the deployment of VASM. So you need to create a target canister for which you will be deploying your VASM beforehand. You can when you upload whole big VASM to the IC, and then you want to deploy it, first you need to prepare a target canister. You can do it from the DFX or from NNS, either way works. However, you need to establish an additional controller for this canister, because every canister has a list of controllers that can read its state and change its state. It's either stop start or reinstall upgrade the full code. So the deployer canister, it needs to be set as a controller for the target canister for this whole thing to work. And as you can see, we are using the management canister. Which is I have no idea how to read it, but it's this one. And on the management canister, you're invoking different functions to manage your canisters. And the one to change the code is install code. And we're specifying all required parties with VASM module. And this part works because actually there is different boundary for inter-canister calls. They can be bigger than the calls from outside of the IC. So the HTTP calls have 2 megabytes limit, and the inter-canister calls have much bigger limit. I don't remember correctly how big. And also one more tricky part is that we need to provide the arguments for the initialization method of the target canister, which are already encoded in Candid. I will show you in a moment how to do it, because it also needs to be done. And yeah, that's actually, this line does it all. Other lines are actually to call the freshly deployed ledger canister. It was actually for the ledger canister. The faucet, I hope you had the possibility to use it. So that's that. It's not like I'm running into this limitation daily, but I'm running into it like always in unexpected parts and in moments I wouldn't like it to. It is a little bit of hack. However, I understand why there needs to be a limit on HTTP size calls. This code I have used 3 or more or 4 times. Yeah, that's it. Most of the time, I'm trying to decrease the size of the canisters as much as possible. You can actually do it in Rust with to some degree, because apart from ICCDK optimizer, we also have optimization flags for Rust, which can strip parts of the code quite efficiently. Actually, this code is not inserted into repo mainly because it's shared with other teams. It's like an internal code, but if you'd like, I can ask and discuss on what we would need to do to make it public. I will also, the limit only 2 megabytes. Well, for definite answer, you would need to ask someone from the Dfinity team. However, I assume that it's mainly because you do not want to have HTTP ports open for long periods of time, because it would be really easy to make a DDoS attack on the whole network. So if you open ports and just stream data without any limits, then it will be quite easy to block the whole network. And the limit, yeah, also, well, because yes and no, they made it like a universal limit of 2 megabytes for both directions. So ingoing and outgoing messages all have a limit of maximum 2 megabytes. And if you need to stream more data than 2 megabytes, it always takes time. And consensus is one thing, but the problem of scalability is another. And you can't really scale things or upgrade canisters if they're locked in sending data. That once again, if you would like a definite answer, I think the best place right now is Dfinity forum to ask. Going back to the uploading, second part of the uploader is the JavaScript file, which is run by Node to upload actual WASM And here is the IDL specification. Some other part, the important part is here. So we are loading our VASM into chunks, and this one splits chunks into 1 megabyte size. Here is the variables for initialization of the ledger canister of this VASM. This VASM I'm uploading, and it will change. Your canister may have no initialization at all, or might have some other variables. So this part needs to be customized for your case. And I've actually had to look at the actor implementation in JavaScript to find this part, because it's nowhere to be found in documentation right now, is how to get the values, the IDL, and get the candid encoded byte buffer. So yeah, it's like this. Your initialization, the candid service, and then you're using encode with the service and the actual values to get the byte buffer of encoded candid, because this buffer is required to actually run the init on the VASM we are uploading. And here is the uploading of the VASM, and here is the deployment. Okay, do you have some other questions? Sebastian, I think that we've reached all the questions that there was. If you have any other questions regarding the Rust or IC in general, you can always find me on Discord. Handle is Stopakor.
All right. Thank you so much.
Okay, you're about putting Java into IC. Right now it's okay? Can you hear me clearly?
But for me, the audio is working fine.
Okay, so just to reiterate, I think you would need to try and find a way to compile Java into VASM. I'm quite sure you won't find any compiler from Java to Rust than to VASM. The only other way would be to find a Java virtual machine that was compiled to VASM. However, I do not believe that the compiler would be good. And Java has its own garbage collector which runs periodically. And I'm not sure that it would be in any way compatible with the IC. Yeah, short answer is that I don't think it will work.
Yeah, I also don't think it's possible right now. Well,
just to, I don't think only right now, but in general at all, because Java is used to be run like on continuous platforms, so it can do anything in the background. On the IC, any method must must take no longer than 400 milliseconds.
Okay. Interesting. Thank you. Yeah, if we don't have any question, it means to build on DIC, you need to know Motoko and Rust. No, Motoko or Rust. You need one of the two. Yeah, Motoko or Rust. There will be a lecture from Jordan last on how to use JavaScript to develop on DIC. It's possible. It's possible. There is a smart contract, a token that was written in JavaScript, but there is some limitation. But the lecture will provide more information.
Okay, so thank you very much for attending, and have a nice afternoon.
Yeah, thank you very much for your time. Have a nice afternoon as well.